Hi, in this video I'm going to show you how to train this face segmentation model from the Archai repo on Azure ML. This model is very cool. It trains on a synthetic dataset that's available here in GitHub that contains lots of different types of faces and different poses, and the model inference will detect what each pixel belongs to in 19 different classes, including hair, ear, face, mouth, lips, nose, and so on. Very cool model. When you run inference, you basically get back this mask. Now this sample for Archai is the neural architecture search library from Microsoft Research. It will set up a search space that tries different model architectures by playing with all of these different architecture parameters. And that's all explained here and implemented in the sample. It also includes how to run the search locally on your machine and how to train a model that is produced by that search. We did this ourselves and came up with this Pareto curve that shows how the model improves over time. Each time it does iterations of the search algorithm until we get the best possible models on this frontier in yellow. This did 10 search iterations. We also show you what the architectures are for those models, both on a CPU and also for Snapdragon targets. So this sample is cool because we actually test the models on Snapdragon hardware, which would be what you would have on an Android phone. And you can see how it found some great models there as well. You can also see what the Snapdragon quantized model latency is when it runs on the DSP processor. And you can see that these models are extremely fast, all the way down to 2 milliseconds per inference, which means that you could run these models on a phone and not kill the battery. So how are we going to do all of this on Azure ML? The main entry point to the Azure ML pipeline here that we're going to set up for running the search is, it all starts with aml.py. There is some README information on how that works in the Azure ML setup instructions, and this is a high-level picture here of what we're going to do. So we're going to run the neural architecture search. That will actually run in Azure ML. It will start Azure ML training pipelines for doing partial training, because the search needs to know how good the models are, but they don't need to be fully trained. Just one epoch is enough for the search algorithm to have enough information to pick the best models. The partial training is implemented using Azure ML pipelines, and we use a blob store for storing the models and the results of that training, as well as a Azure table to coordinate this whole remote async process here. We also can do remote device inference testing on those Qualcomm devices, and that whole pipeline is going to run here as well. Let's go. This is actually creating some Azure ML resources, including the CPU cluster, GPU cluster, the Conda environment. It then uploads the various bits of source code that we need to run the search in the cloud, and it's handy. It'll open the actual Azure ML Studio. Now you'll notice that the Azure ML pipelines are clever. There's a little recycle sign on this component because the data preparation part of the pipeline, which is basically creating my data set in my Azure storage account, has already been done before, so it just recycles that node saying that's already completed. It's now setting up the Archai search job. And what you'll find yourself doing a lot with Azure ML Studio is you'll double click a component and click on output logs to find out what's going on. And you can get all kinds of information. Right now it's just queuing the job. So we'll grab a cup of tea and come back and see how much progress it's made. Alright, cool. We can see that the job has been scheduled on our CPU cluster and is now running, which means we have a bunch more logs here. So all these system logs, but the important one is the user logs. That's the output of your job, our job, the search job. So it's made some progress. Let's see what's going on here. First up, we can see that it is loading our search configuration that's been mounted to a local drive, a local folder here. And it's now going through and creating some Onyx models. This is for local Onyx inference testing. latency testing. But then it's going into calculating our Pareto curve from those models. And we can see an interesting thing here. We can see that it has found in our Azure storage table, these models already exist and they already have inference numbers on them. So we don't need to rerun them. And that's a fun thing about this entire process, is it's fully restartable. I can kill this whole Azure ML pipeline and restart it and it'll pick up where it left off. But it's already got that, so it's going to go ahead and start training. So this is our search plugin, which does Azure ML partial training of these 20 models on our GPU cluster. And it is copying the source code needed to do that training, and it's launching all of these jobs in an Azure ML pipeline, and is now waiting for that pipeline to finish. So if you go over to pipelines now, you'll see two things. You'll see the searches running, but you'll see a training pipeline has been kicked off. Great. Let's see what's going on there. Whoa. So this is 20 models that are going to be trained in parallel, all using the same data set as input, of course. This is happening on a GPU cluster so that we can get maximum throughput. Each one of these training jobs is independent, so it's training different model architectures. And we can see this one just turned blue, so it's been scheduled already, and we can go. Same thing, like I said before, and look at the output logs. So again, you can see it's running, so we should get some user logs here showing up real soon. So we'll grab another cup of tea, come back and see how training is progressing. Okay. Looks like training is indeed progressing. We're 50% of the way through this first model already. And while this is happening, you can also go over to your Azure storage table and hit refresh, and we should see some status here. What you'll find is a status of training. So that shows you that these are the models that are being trained. When training is finished, we're going to publish the validation IOU metric. Will show up in this table. So you can monitor that. There's a fun little filter you can do with the Azure ML table. You can say, status not equal complete, because eventually when 10 iterations are completed, we're going to have hundreds of models in this table. So you want to look at just the things that are not finished. You can do this simple filtering here. Okay, cool. This first training job has completed. It shows green, and the output log shows that it got to the end, the 100%, and as some metrics here. So the metric that we're going to remember is this one. We're going to store that in our Azure table under this key. So this shows you the script telling us that it did that. If we go over to our store, we can actually say name equals that key to find that row, and we can see that the status of training has been changed back to complete, and we have a new metric. So this metric now stored in this table can be communicated back to the search pipeline when all the training jobs are finished, but they're not all finished yet. If you go back and hide the overview, you can see there's lots of other training jobs still yet to be done. So we'll have another cup of tea and come back in a second. Cool. All 20 training jobs are now completed, so the overall job status of the training pipeline is complete. It completed the training in 3 hours and 30 minutes. We can now go back to our search pipeline and see what happens next. Here's the search pipeline, and the search is still running. Go to the output logs, and we can see, if we scroll back a bit here, we can see what happened. So the previous search results have been printed here, showing all of those validation IOU metrics from the first 20 models. That then goes back into the evolution Pareto search algorithm, where it now mutates the models to come up with some new models. So this is where it's mutating. And now we have all these new models, checks the Onyx latency quickly, and kicks off another remote Snapdragon inference testing. We'll see that if we go over to the store and look for models that are not complete. We can see all of these new models showed up, and it's quantizing, and it will soon, when the quantization is done, it will soon start doing inference testing on these models on the Snapdragon hardware. I can jump over to the machine that's connected to the Qualcomm hardware. I actually have 4 Qualcomm boards connected here, and we have some remote screens running. This one is doing quantization, and the other one will be waiting for quantized models that it can test. So it's in an idle loop here, waiting for that quantization to finish. So we can go back to the big picture and we can now see all of these things are running. We can see the training is happening in Azure ML pipelines, the remote device inference testing is happening. And we essentially have this fun distributed system that's working its way through an evolutionary Pareto search for the best possible model architecture. So we can see that with about 3 hours per training run for all 20 models and 10 iterations of the search algorithm, it'll take about 30 hours to complete this work. But of course that's a lot better than not having parallel training. If we had to serialize those 20 models, it would take 600 hours. So we're getting a nice speed up here using Azure ML. There is a notebook in the AML folder called results, which you can use to take a look at all of the search iterations once they've completed. First thing you need to do is install a couple pip modules that we use in the notebook, Bokeh and Selenium. I've already done that, so it should be quick. Then what we do is we connect to the Azure store where we have all of the results and we download them. All of the rows that are complete, that is, anyway. We found 1900 rows. That doesn't mean we train 1900 models because we also have rows for things where we only did ONNX inference testing. Sometimes it'll do an ONNX inference test and realize the model's not worth continuing with, and so those will be discarded. But the ones that have complete metrics is what we want to look at. We'll create a nice little scatter plot with Bokeh, and then we'll run and take a look at all 10 iterations, comparing the Qualcomm inference time against the validation IOU metric, and we'll also compare the ONNX CPU inference time against that same metric. So we'll have two charts here produced for each iteration. Go ahead and run that. This is iteration 1, and you can see how it builds over time. Now we're also generating some PNG images of each of these iterations on your hard drive so that you can look at them all together. So what we'll do now is we'll load up all 10 iterations of just the ONNX results so that you can use the arrow key now and watch the build. The key thing here is that if we go to the end, the darker colors, there's a color gradient here from iteration 1 all the way to iteration 10. And then we've highlighted the Pareto curve in yellow just so it pops out and you can see what the best models are with regards to the trade-off between validation accuracy and ONNX inference time. We can also look at the Qualcomm numbers, and I'll load that up. So Qualcomm inference time over here all the way down to 2.5 milliseconds. What you can see here is that the initial iteration did sort of a splatter across your search space. It found a bunch of models that are not interesting down here, but the Pareto curve models, the yellow ones, were then used to evolve and mutate into potentially even better models. So instead of just randomly shooting, and wasting lots of time with all these models down here, we use the evolutionary Pareto curve algorithm, which will mutate these successful models and see if we can improve them. And indeed we do, right? We find some new yellow dots showing up on each iteration. It's incremental, you don't see a huge amount of new yellow dots, but you do see new Pareto curve getting pushed out on every iteration all the way up to iteration 10 here. And now what we've got is a nice collection of models which you can then give to your customer, because the customer may need to pick any one of those models depending on their business needs. If the business needs can spend this much inference time, then that model's the best, but they might have an inference budget that's down here somewhere keeping up with real-time video or something, right? And so you need to get it, or you need to reduce power usage, in which case somewhere over here on the Pareto curve might be best, right? So clearly there's a drop-off in accuracy at some point, but once you get past this point, there's a nice bunch of models in here that might fit your business needs. So that's why Archai produces that Pareto curve. So I think this shows that Archai works, right? And the interesting thing to note here is we're talking about a big spread in models, both in accuracy, 40% to 80%, that's a range of 100% increase in accuracy. And we're talking about inference times from 2 milliseconds up to 14 milliseconds. That's a 7 times factor. So this spread is much bigger than anything you're going to get from hyperparameter tuning or any of these other ways of optimizing models. This is the big search of what's possible with different model architectures. Once you now find this Pareto curve and you've pick a model here that you really like, you can then go and do hyperparameter tuning and other optimizations, quantization and so on, to improve those models further. But I think Archai kind of sets the table in terms of what's possible with this type of model architecture. So that's it for my demo. I hope you check out Archai on GitHub. There's a really nice documentation page here that will take you through how it works.